go. And okay, let's just really quickly take a look at the blog here. So today we're doing part 2 of implicit differentiation. Today's kind of a little meatier lesson, a little more meaty lesson than yesterday, a little more important. And once we're done today's lesson, we'll do some more examples tomorrow. So we won't get through all the examples in one class, I don't think. But by the time we're done today, though, you can start in on this assignment. It's kind of a bigger assignment, so this is pretty much going to take us through this week, and maybe you might even be working on it over the break. I also have a couple of handouts for you that I'll get to you in a sec. I also have, I think this is the group that I still owe quiz 2 from last unit 2, yeah. And quiz 3 I'm still working on. Cool. That's what's going on. We are going to kind of use Teams here every day this week, and I want us to try to get used to OneNote. I am going to try to get you guys to submit a little quiz to me over the learning from home session using OneNote. If it doesn't work for you, we still have EDSB. Remember, everybody was here last semester. I'm sure you submitted things to your teachers on EDSB. But OneNote's better because OneNote I can actually take what you hand to me and actually mark it like it's a normal test because I have a touch screen that I can write on and then send it back to you and it just looks like I wrote on it in red pen or whatever. It's really, really efficient way to do things. Anyway, excuse me. Let's get OneNote open. If you manage to find this, great. If not, you can just jot some things down here. That's actually not the file I want. Is this the file I want? Nope. Is this the file I want? There's the file I want. Okay, so I'm into implicit differentiation part 2. You don't have to write all these instructions down, especially if you can find this on your OneNote. But this is actually just a continuation of the same example we did yesterday. So if you did the notes from the assignment yesterday, really all you have to jot down is that we're starting method 2. We're still using the same example of x squared plus y squared equals 225. And when I see an x squared, y squared, where those x squared and y squared aren't being divided by any number, there's no fractions for coefficients on those two things, I generally know it's a circle. And this is a circle with a radius of 15. So we could make ourselves a sketch of that. Make that a bit bigger. There we go. And method 1, we took the equation and we rearranged it so that it was y equals. That gave us kind of a plus and minus version of the equation. We decided, well, we need the plus version. But now we're going to do it a different way. We're going to do it without isolating the y value. And we leave the equation where y is implicitly defined in the relation. And that's what we call implicit differentiation. So the equation again is x squared plus y squared equals 225. So if you're just writing this as notes, you can just write method 2, x squared plus y squared equals 225, and make yourself a quick sketch of that circle. And of course, we want to know where, let's see, what does the actual question say? We want to find the slope of the equation of the circle at the point where x equals 9. So when x equals 9, so let's see, that's about, let's see, about there. And there's going to be 2 points where x is 9, where I'm going to have some sort of tangent line. I'm freehanding tangent lines here. Oh, that's not too bad. I don't mind that. So we're looking for those two points, right? We want to know the slope of those 2 lines right there at the point where x equals 9. I think maybe the first thing I'll do is figure out how much y is. So this is 9 comma something, and this is 9 comma something. Let's figure out the somethings. So if x is 9, I have 9 squared plus y squared equals 225. So y squared is equal to 225 minus 81. Let me get a skinnier pen here. There we go. So y squared is equal to, let's see, that would be 144. So y is equal to plus or minus 12. So there we go. So this one's 12, and this one's negative 12. So there's the first part of this thing solved. Now, like everything else we've done this year, if we want to find slope, we need to find the derivative, right? We need to find dy by dx, which is the same thing as saying the rise over the run, which is the same thing as saying delta y over delta x, which is the same thing as saying slope. All these things mean the same thing to us. So we're going to find the derivative of this. All right, so how are we going to do that without rearranging it? Well, usually I write it like this. I'm trying to find dy by dx. So I'm actually going to find the derivative with respect to x of this entire equation. Like so. Excuse me. All right, well, the first part, the derivative of x squared, that's pretty easy, 2x. And for the second part, this is basically chain rule. The derivative of y squared is going to be, well, I treat it like, it's one of those substitution chain rule questions, right? So it's the derivative of the outside, 2y, times the derivative of y itself. Now, I don't have y explicitly defined, so I'm just going to say it's the derivative of y with respect to x. And of course, the derivative of the other side of the equation, the derivative of any constant, is just 0. And let me tidy that up a little bit. There we go. Now, this is kind of the key to implicit differentiation right here. It's a little like in English when you get to use a noun as a verb, right? Sometimes that's grammatically acceptable, but I remember my English teacher in high school cringing about that. He said, oh, this trend in modern writing to use nouns as verbs, like people saying that they're going antiquing, right? I wonder what he thinks of it now, because now that's way more common. I hear that kind of as common language nowadays. People go, oh, what happened on the test? I forgot how to algebra. You know, people use nouns like they're verbs. This thing here has always been, so far in our course, an instruction. It's what it's been telling us to do something. It's an operation, right? It is the derivative of equation y with respect to x. It's the slope of the line y at the point x. Well, now, I'm going to actually treat this thing like it's a variable. After all, that was the thing I wanted to solve in the first place. So I'm going to treat that thing like it's a variable. Oops, go away. So 2x plus 2y times dy dx equals 0. Let me write it again without the highlighter in the way. I'm going to isolate dy dx. I'm going to minus 2x from both sides. I'm going to divide both sides by 2y. And that's going to give me, the 2's cancel, so it gives me negative y over x. And this thing here is, again, the equation of the slope. So everywhere around that circle, that's the equation of the slope. Of course, I'm just going to move over this way, give myself some room. Actually, I've never tried this. I should be able to, whoa, that's not what I wanted to do. No, don't do that. Undo, undo, undo. There we go. If I put the cursor here, can I maybe? No, that's just bringing up stuff. What if I put it there? No, move it up a little bit more, put it there. There we go. There we go. I just wanted to give myself more room to write. There. Okay, so anyway, like I was saying, this thing here represents the slope of the circle, of everywhere around the circle, and I want to know the slope at the point 9 and plus or minus 12. So, therefore, my slope, which is again the dy by dx, is negative x over y, which will be negative 9 over 12, or, if I plug in the other one, negative 9 over negative 12. Either way, those two fractions simplify to negative 3/4 or positive 3/4. And that kind of makes sense with my picture, right? Because remember, I have two lines. So this one has a slope of negative 3/4, and this one has a slope of 3/4. And just to make sure I'm on the right track, let's check out with Desmos and see if Desmos agrees with us. Now we're actually kind of getting to the limits of what Desmos can do. Desmos can do simple derivatives. It can't do implicit differentiation. So we kind of still have to do the implicit differentiation ourselves. It doesn't know how to do these steps in here where I had to put the derivative function in and then treat it like a variable. It can't do that. But it can still do everything else. It can, let me just go to my Chrome here, and there we go. It can graph a circle, no problem. Of course, it's kind of too big for the screen right now. There we go. Graph a circle, no problem. I can put down the points that I found. There we go, 9, 9, 12, 9, negative 12. And if I did this right, of course, I never actually showed this. Let me just go back to my work for a second. I didn't actually get to the actual equation, so y minus y1 equals m times x minus x1 would give me the equation of those tangents. And at the point 9, 12, it's going to be y minus 12 equals, so hang on a sec, let's make sure we got this right. The one where 12 is positive is up here. So the one where 12 is a positive is the one where the slope is negative, correct? So that's going to be negative 3/4 of x minus 9. And the other equation is y plus 12 equals positive 3/4 x minus 9. So I'm going to put those two equations into my Desmos. And here they are. And there we go. Feel free to zoom in to sort of see, yep, that definitely looks like a tangent line. And that's how you can still use Desmos to check. It can't do the calculus for you anymore, but once you get an answer, you can still check to make sure it's reasonable. If you were off, if you'd have made a little mistake, then something would be wrong with these tangents, like the line wouldn't quite look like a tangent on the screen, or it would miss that point that you had plotted. Okay, so that's the first example, which is basically the same example as yesterday. Let's move on to a second example. So copy this one down. Example 2. Determine the slope of the tangent to the curve x cubed plus y cubed equals 9 at the point 2, 1. So, and feel free, how about you give it a try? All you have to do is start the same way I started the last one. The derivative with respect to x of the entire equation, which means you have to do the derivative of the left side and the right side. And the tough part is that this part right here is going to need a chain rule. That's the part that makes this implicit differentiation. Okay? While people are trying that, I'm going to hand some stuff out. So guys at home, I'm going to move away from the microphone for a minute. Maybe I'll pause the video while I'm at it. And we're back. Okay. So, how do we do this? Well, the derivative of x cubed is, oops. Let me undo that. Let me try that again. Derivative of x cubed is 3x squared. The derivative of of y cubed is 3y squared times the derivative of y with respect to x. That's how the chain rule works. And of course, the derivative of 9 is nothing. What do I want to do? I would like to isolate for that derivative because that's what I'm looking for. The slope is the derivative. So I'm going to minus 3x squared from both sides. I'm going to divide both sides by 3y squared. I'll divide the 3's with each other, cancel those, and there's my equation. Okay. And I want to know how much that slope is at the point, I've already forgotten the point, 2, 1. There we go, at 2, 1. So I can plug in 2, 1. So the derivative at the point where x is 2 is plug in 2 for x and a 1 for y. And make sure you understand that this negative here and here is not part of the base, right? I'm not squaring that negative. That's like saying negative 1x squared. So make sure you understand that. That's a really common mistake people make with negatives. All right, so that's going to give us, negative 4. And that's my slope. All right, let's see if that's what it looks like on Desmos again. So going to Desmos, there we go. So let's see. First of all, what kind of curve does this thing make? Oh, interesting. Makes kind of like a, let's just go to home. There we go. Makes kind of like a diagonal speed bump. So that's what x cubed, y cubed curves look like. And we were trying to find the slope at that point. And I found that the slope was negative 4. So putting negative 4 into the equation, this should make a tangent at that point. And as you can see, it does. Looks pretty good, actually. Tangent point. Okay. All right. Next. And copy this one down. We'll call this one example 3. And make yourself a little sketch here. Find the slopes of the tangents to the ellipse when x is negative 4. And notice the plural on tangent. Tangents. Why is there more than one tangent? Because the ellipse happens to have 2 points when x is negative 4. Here and here. So maybe just make a quick sketch of this. So there's a tangent line that's going that way, and a tangent line that's going this way. And I want the slope of those 2 lines. Okay? So jot that question down. I'll give you a sec. All right. So I always start with this. I always start by saying I'd like the derivative of the entire equation. Okay, and then I start finding those derivatives. So the derivative of 2x squared is 4x. The derivative of y squared is 2y times dy dx. And the derivative of 36 is 0. Okay. You know what? I'm actually going to do this one a little different. Instead of dy dx, let's use the other notation. I don't usually use this when I'm working, but some textbooks do. Instead of dy dx, you can still use y prime. If you like y prime better, go ahead. I'm notoriously bad for forgetting to write my prime, so that would look like 2y times y if you forgot the prime. But it's certainly fine to do it this way. Okay, and I want to know what y primed is. I want to know the derivative. So y primed would equal minus 4x from both sides, and divide both sides by 2y. So y primed is negative 2x over y. Okay, and we want to know what happens when x is negative 4. So first of all, maybe we should figure out how much y is when x is negative 4. So 2 times negative 4 squared plus y squared is equal to 36. So that's 16 times 2 is 32. Negative 36. So y squared would equal, oh wait a minute, why is that a negative? I don't know. That's not what I meant to write. There we go, thank you. So y squared is equal to 4, which means that y is plus or minus 2. So that means when I go back to my slope, if I want the specific slope at a point, in this case the point is x is plus or minus, or y is plus or minus 2, so this is negative 4, 2, and this is negative 4, negative 2, right? So I have to find 2 different slopes. So one slope here would be when y is negative 2. So that would be negative 2 times negative 4 divided by negative 2, which is, that'd be negative 4. And my other slope happens when x is negative 4 but y is positive 2. So my slopes are 4 and negative 4. And again, one last time here. We can check that out on Desmos. So let's see, go close, close. So there's the ellipse. There's the first point. There's the second point. And I just turned those slopes into equations. Do they look like tangents? They certainly do. So there we got it. Okay, everything we've done so far today, we could have done with method 1. Right? It wouldn't have been that hard. Wouldn't have been that hard for us to look at, oops, oh, undo that. There we go. Wouldn't have been that hard to look at this equation here and rearrange it so that it's y equals plus or minus something. Okay. Next example, that wouldn't be as easy. Check out this one. Y happens in 2 places in the equation. So that's not going to be so easy to isolate for y. So we're not going to. We're going to use implicit differentiation. Method 1, I wouldn't touch with a 10-foot pole with a question like this. So this is going to be for sure done with method 2. So I'm going to take the derivative with respect to x of x cubed plus x squared y plus 4y cubed equals 6. So I'll give you a sec to catch up to me in the writing here. Sip of my coffee. I don't even know what kind of curve this is. Trying to picture it in my head. What kind of curves are x cubed, y cubed, and an x squared y term? I don't know. Might be another speed bump looking thing. We'll see. I'll graph it in a minute. All right, so from here, let's do the derivative. Derivative of x cubed is 3x squared. Derivative of x squared y, what am I going to use for this thing? Any ideas? Say that again? It's going to be chain rule and chain rule together with the y makes it a chain rule and product law because x squared times y is really to me a product. So product law says I take the derivative of the first thing times the second thing plus the first thing times the derivative of the second thing. Then keep on down the road here. The derivative of 4y cubed is 12y squared times the derivative of y. And as always, the derivative of a constant 0. Now what am I going to do? Well, remember my goal is to find this. And it happens twice in my equation, here and here. So I'm going to have to actually isolate that. So anything that doesn't have, any term that doesn't have that derivative in it, I'm going to leave on this side of the equation. So x squared times dy dx plus 12y squared times dy dx is going to equal, and I'll move the other things to the other side, so negative 3x squared minus 2xy. And then what tool in the toolbox can I get? Because remember, I want to isolate dy dx. I'm going to factor. So I'm going to factor dy dx out of the left side. Everybody see what I'm doing algebraically? And now I'm going to divide both sides of the equation by this factor, which will isolate the derivative, which is what I wanted to do. So, oops, I keep forgetting to shut off the highlighter. So the derivative isolated is negative 3x squared minus 2xy all over x squared plus 12y squared. That's the equation of the slope. Okay? Now, this one just wanted the derivative, so that's it. The question's over. But it'd be nice to be able to do a check, so I'm going to try to do a check. Let's see if I can do one. Again, Desmos, let's see if you can help us out. First of all, let's graph the original thing. So the original thing was this kind of wacky looking curve here. And let's see. I was right, it's another speed bump looking thing. Okay, so I notice as I look at it, hey, look at that. It looks like it goes right through 1, 1. And I could, oops, oh, go back. There we go. And I could actually go back to the equation, and you can see if you plug into the equation x is 1 and y is 1, you get 1 plus 1 plus 4 is 6. So yes, 1, 1 works. Now, this is a little bit of luck on my part. There is, of course, the possibility that you get an equation of a curve that there's no quick, easy integer answers that fit the curve. But in this case, I know 1, 1's a point, so I can actually find what the slope is at 1, 1, and I think I'll do that real quick here. Just let me go back to Onenote. There we go. So at 1, 1, dy dx would equal -3 minus 2 all over 1 plus 12, which is -5/13. So the actual equation of the tangent at that point would be y minus 1 equals -5/13 times x minus 1. So again, go back to my Desmos, and I'll actually graph that. So there's the point. This better be a tangent. Looking good. Looks like it is. So there we have it. A fancy curve that I would have had a pretty hard time using method 1. And I managed to get, I managed to get the derivative. Okay, that's about as far as we'll go today, which is good because we got like a minute left. Guys who have to go to band should probably start packing up. And here again is what it says on the blog. You actually have some questions you can do now. Right there for 2.7 and 5.3 questions. We'll do some more examples tomorrow. So tune in tomorrow on Teams, and I'm gonna also try to learn how to do. They're gonna make us do attendance on Teams during our Learn from Home. So I'm gonna try to do that tomorrow too, just as a practice run. All right, I'm gonna stop the video. If anybody has any questions, I'm still taking questions on antiderivative stuff. All right, let me stop the video.